Hello, and welcome to my SIGTYP talk. Today we're going to be talking about investigating information-theoretic influences on the order of elements in natural language. So let's get right to it. Here is the big question, the big picture question behind this work. We want to know, what is natural language? How would you mathematically characterize this thing that we call natural language? And this work is part of a broader argument that we can characterize natural language in terms of a code, a communication code, which enables this kind of communication among agents. So you have agent A here, who encodes some kind of meaning into an utterance by speaking, sends it over to agent B, who then receives that utterance, decodes it, comprehends it back into agent A's intended meaning. So natural language is a communication code that enables this kind of communication. But if we consider natural language within the context of all the possible codes which could exist for communicating information, things like Huffman codes in computer science, or things like DNA in the natural world, these natural systems that communicate information, we find that among that space of possible codes, human language is actually unique and particular in a number of different ways. So human languages occupy a very particular subset of that space of possible codes. Human languages have properties like, say, compositionality, which not all codes have. So what is it that explains and characterizes human languages, the shape of human languages within the space of all possible codes? I'm arguing that what characterizes human languages are the constraints that they operate under. Human language has to operate under the constraint that it enables human agents, with all of our limitations, to encode and decode meanings easily, given our cognitive systems. So it's a communication system subject to these constraints. And my argument is that this is what defines the characteristic properties of human language. So here's the standard information theory worldview when it comes to codes. You have an information source, that's whatever generates your distribution on meanings you want to communicate about. You have a transmitter which encodes that into a signal. The signal goes through a medium, the signal is then received and then is decoded to the destination. Each point in this graph is a location where constraints can exist. So maybe a code has to operate under constraints on the encoding process, or maybe on the decoding process, or maybe it has to enable communication through a noisy channel. In this talk, I'm going to be focusing mainly on constraints that exist here in the decoding process, which in terms of psycholinguistics is the online comprehension process. That's not because I think constraints that live at other parts of this graph are not important, far be it from that. In fact, I think they're very important. But when it comes to comprehension, we have very good quantitative mathematical models of human language comprehension, which enable us to make a lot of predictions. So I'm focusing on comprehension here, not because I think it's the most important thing, but simply because as of the year 2021, in my opinion, that's where we have the best models, the most useful models. So the idea is to view each human language as a particular solution to the problem of maximally efficient communication, subject to fixed human information processing constraints. So the process of encoding messages, decoding messages, and learning. These are information processing constraints particular to humans, and human language is a code that enables communication subject to those constraints. So the efficiency hypothesis is a truly ancient idea in linguistics, which is that human languages are the result of a process that maximizes communication while minimizing the complexity of production, comprehension, and learning. To put this a little bit more mathematically, here's the kind of research program that I'm advocating for and that I'll be presenting examples of in this series of talks. So imagine that you can arrange all the possible codes for communication on a line like this. Some of these are going to look like natural languages and some of them will not look like natural languages. And let's imagine that we can score every language according to something like its efficiency. So this is an objective function, J of L, which is going to have a form that's something like complexity, which is bad, minus informativity, which is good. And we're going to be trying to minimize this function, so that means effectively we're maximizing informativity, minimizing complexity. So if you can imagine thinking of this space of languages and their scores on this objective, the idea is that we want to define this objective in terms of complexity and informativity such that the minima correspond to actual descriptions of natural languages, English, Mandarin, Walbury, whatever, some language which is maybe not attested but seems like it could be attested. Each minimum of this objective should correspond to something like a natural language within this research program. So if we want to pursue this efficiency hypothesis, we need to develop theories of information processing difficulty in language. What are those constraints on comprehension, production, and learning? You want to have models of those which you can actually validate against psychometric data. And then you test predictions about them, not only about your psychometric data, but also about the qualitative and quantitative properties of language as you can observe it in a corpus. This talk is going to focus on predictions within this paradigm about how information is structured in time in utterances, which is to say it's going to be about patterns of word order and also orders of other kinds of elements, both within and across languages. Okay, so within this paradigm, I'm claiming that we can see natural languages as codes for some kind of meaning, which is expressed, which is sent from one agent to another. Well, what is that meaning? What is the meaning which is expressed by an utterance or by a sentence? How would you characterize that? That's very difficult. We don't really have great ways of characterizing that, ways that are complete enough that they can give us a real quantitative theory. So let's think about the meaning which is expressed by this sentence. And I'm actually not going to try to provide an idea of how to characterize the meaning of something like this sentence, but rather I'm just going to be focusing on a part of the meaning. So if we want to figure out the meaning of the sentence, whatever that meaning is, we can we see that it's related to the words in the sentence in certain ways. So for example, the word long here is modifying the word letter here. So in the meaning of this sentence, the longness pertains to the letter. And we also see that the meaning of the sentence, whatever it is, it involves something like a writing event, and that writing event involves an agent who is I and a patient, which is the letter. It has a subject and an object. So without saying what the actual representation of the meaning is, we can note that in that representation, the meanings of the individual words will be related to the meaning of the whole in some certain way. And that's approximated by dependency relations. So we can say that long is modifying letter because it's the letter that is long here, not the friend that is long. And we can say that I and the letter and the to the friend stuff, those are in some sense modifying the verb wrote. So this gives us, and we can complete the graph here, and it can continue this tree to contain all the words in the sentence. This is a dependency tree. Dependency tree is a representation, usually taken as a representation of the shallow syntax of a sentence. But I'm going to be thinking about it here as a sort of proxy for the meaning of a sentence. So you can see one aspect of the meaning of this sentence as being this unordered dependency graph here, which expresses this network of relationships among words and the types of those relationships. So if you want to recover the meaning of the sentence, whatever that is, you need to recover this network of relationships among the words and their types. So now viewing this unordered dependency tree as a sort of proxy for the meaning encoded by language, we can then think about language as a function from these unordered dependency trees to linear strings of words which realize those trees and express the information in those trees. So for example, for this unordered tree, wrote letter to friend, fragment of a tree, the Arabic language, for example, corresponds to one way of linearizing that tree in one particular order. So in this case, an order where the verb goes initially. A language like Japanese corresponds to another way of linearizing the same tree. So in general, I'm going to be thinking about the grammar of a language as it pertains to word order as a function L, which takes in an unordered dependency tree and gives you out a distribution on strings linearizing the tree. And I'm going to be thinking about these word order grammars L. Instead of languages in general, this talk's going to be focusing in on just word order grammars in this sense. So instead of answering the big question, which would take like a lifetime to answer, instead of characterizing just human languages within the space of possible communication codes, what this reduces to is looking at the word orders of human languages within the space of possible tree linearization algorithms. And what would we want a theory of word order like this to explain? Well, there's two kinds of things we'd want it to explain. The first thing is it should explain qualitative universals of word order that have been documented by linguists and by typologists going back, decades and decades. So it should capture the distinctive word order patterns of human languages. And we also want it to capture the quantitative statistical properties of word order as you can see it in text. So not only getting the qualitative stuff, but also the quantitative stuff you can see in a text. Now, in the rest of today's series of talks, I'm going to be covering three main topics. First is how memory constraints can affect this linearization process. Second is I'm going to be presenting an information-theoretic model of language comprehension, which is going to derive a more general form of these memory constraints as they affect word order. And we're going to validate some of the predictions of that model, in particular a prediction called information-locality. And then we're going to, in the last content section here, optimizing languages, I'm going to show a case study where we actually just directly implemented this optimization approach to explaining word order. We literally have informativity and complexity, and we literally optimize the function, and we get stuff that looks like languages. So let's go into memory constraints now. Now, one of the main ways that memory constraints, and by that I mean the incremental memory that we're using during language comprehension, one of the main ways that memory constraints affect languages is through this phenomenon called dependency locality. I'm going to give a few examples here that get you used to this idea of dependency locality. So, here's a sentence. Bob threw out the trash. I'm going to give this a thumbs up. The thumbs up means that this is a sentence that is good. It's easy to understand, so no one would really have trouble understanding this sentence. And we note that a dependency exists between the words through and out. And what that means is that to understand what the word out means in this context, or even what the word through means in this context, you have to consider these two things as a unit. So these two things have to be considered simultaneously for you to understand the sentence. This is what we call a phrasal verb, or a verb particle construction. We can also say, Bob threw the trash out. That's another thumbs up for English, so English speakers won't have any trouble with this. And this shows that these words in a dependency don't have to be contiguous. They can be somewhat separated. There's variability in where you place the particle out in English. Now we can say Bob threw out the old trash that had been sitting in the kitchen. Again, that's fine. Thumbs up. No one would have any trouble understanding this. But then this version of the sentence seems a little bit weird and bad. So Bob threw the old trash that had been sitting in the kitchen out. And it gets even worse if we make that noun phrase in the middle longer. So if we say Bob threw the old trash that had been sitting in the kitchen after the party that he threw yesterday where everyone came but a few people were late out. Now it's nearly incomprehensible, right? And we think part of the reason this sentence seems weird and bad, it has to do with this long dependency that we've created between the word through and the word out. So imagine that you are hearing this sentence word by word, or imagine you're reading it word by word. You're going to have to hold in your memory some representation of the word through, all the way from where you hear it, all the way to the end of the sentence when you get out. And at that point, you can combine your representation of the word through with your representation of the word out to get the meaning of the phrasal verb. But we think that when you have to hold that word through in memory for a long time, that causes difficulty. When you get to out, you have to retrieve the meaning, the representation of the word through. From memory, that retrieval operation might be difficult. It might be inaccurate. And we think it's going to get more difficult and more inaccurate when you had to hold it in memory for a long time for various reasons. This is called the dependency locality effect. The dependency locality effect refers to measurable processing difficulty, which is associated with these long dependencies in text, and it has to do with your working memory. Now, if you're a German speaker, or a Dutch speaker, you're probably looking at this and saying, oh, well, the German language forces you to use number 4 there. The German language forces you into the long dependency. Well, don't worry, we're going to talk about German. We're going to talk about German. And dependency locality effects do exist in German, although they're interestingly different. So in terms of dependency locality as a sort of information processing pressure that's affecting the form of human languages, what does this mean? There's a very simple prediction here. If languages are efficient in this way, they should minimize dependency length. The word orders should be such that words that are in dependencies are close to each other. That makes things easier to understand because now you've just avoided these difficulties that have to do with long dependencies. And there's a long tradition of work that uses this idea going back to the 1980s, using this idea to explain different language universals, including a large subset of the word order correlations that were documented by Greenberg. It's also been used to explain preferences like to put short constituents before long constituents in certain languages. And also there has been a claim that this might be able to explain why crossing dependencies are so rare in natural language. So this is a sort of venerable idea. And what I'm going to be presenting right now is actually some new corpus evidence that has bearing on this idea, which will also demonstrate many aspects of my approach. So we want to test this idea that natural languages are shaped by a pressure to have short dependencies in dependency treebanks. We're going to be using universal dependencies data sets in this and in other studies. In this series of talks, we're going to be using universal dependencies data sets. These are hand-parsed corpora of many languages, many more languages. An incredible amount of great work has been done to put this together. It's like one of the most exciting resources for quantitative syntax ever. So the goal of UD is to apply the same annotation formalism, the same syntactic formalism to all languages. And it looks something like this. Here's an example from the English Universal Dependencies Tree Bank. I ran across this item on the internet. So you get words, you get part-of-speech tags for the words, you get this dependency tree over the words, you have labels on the edges of the tree. Now, if you look at this, this might seem a little odd to you if you're a linguist and you're not used to universal dependencies. In particular, and this consists of like newspapers and blogs and many sort of government documents. And some spoken language. It's mostly written language in universal dependencies. So anyway, if you look at this tree, there's some parts that might seem weird if you're a linguist and you're not used to this. So what's going on with this on the internet part here? So on, the preposition there is actually parsed as a dependent of internet. So the lines here are drawn from head to dependent, and this parse might seem kind of strange. You would usually, in syntax, think of on as the head of a prepositional phrase, which has internet, the noun, as its dependent. And so the UD project has very good reasons for parsing things in the way they did. But for the purpose of this studies and for the purpose of all the studies I'll be showing in this work, we can actually automatically transform the UD annotation to something that's more like syntax as it's typically done by linguists. So we can transform this into something that looks like this, where the prepositions are the heads of nouns and not the other way around. So now we can get tree banks of very many languages. This is a list of the languages that are used in this particular study that I'm presenting now. You can see that UD, at this point, it still is majority Indo-European languages, but there's a lot of interesting stuff here. This is certainly the most diverse sample of parsed corpora that you're going to get. So there are interesting things here like Turkic languages, East Asian languages, Austronesian, Afro-Asiatic, and so on. Now, how would you use tree banks like this to test this idea of dependency locality? Remember, dependency locality in word orders, the idea that word orders are under a pressure to keep words in dependencies close. So let's say we start with a tree. So here's the dependency. This story comes from the AP. This is the first sentence in the English UD tree bank. We can annotate the dependency length of all the dependencies in the sentence. And so what I've done here is I've just given a length to each dependency. That's just the number of words that it traverses. And you can have an argument about what's the right measure of dependency length. Is it the number of words you go over? Is it the number of syllables you go over, or the number of phrases? They're all very correlated. All the ways of measuring dependency length are very correlated with each other. And measuring simply the number of words is an acceptable approximation to whatever the true notion of dependency length should be. We can add up these lengths and say that the total dependency length of this sentence is 6. That's just 1 plus 1 plus 1 plus 2 plus 1. And now we can plot this dependency length, this sum dependency length, in a space where we have sentence length on the x-axis, dependency length on the y. So it's going to go there. So a sentence length 6, dependency length 6. And then we can plot the average dependency length per sentence length in the whole corpus. So as the sentence length goes up, the dependency length also goes up at some rate. You have a sort of growth rate of dependency length as a function of sentence length. Okay, so we can get this curve. This curve is sort of characteristic of the dependency length of English, but we want to actually test this scientific claim that word orders are under a kind of pressure to have short dependencies. So in order to test that claim, we need to compare against what we think language would look like if it were not under a pressure for short dependencies. So if these tree linearization algorithms did not have dependency locality as a constraint, what might they look like? And we can come up with lots and lots of different random baselines instantiating different assumptions about what a tree linearization algorithm might look like if it didn't have dependency locality as a constraint. One of these would be this random baseline here, which I'm calling the projective baseline. This would consist of all the linearizations of the tree which respect this constraint that the dependency lines don't cross, that they are projective. And so what this tells us is if there is actually no pressure for dependency locality in word order, but there is a constraint that says the dependency lines should not cross, then what might this sentence look like? So each sample of the random baseline here says, what might this sentence look like in a world where word order is shaped only by the constraint of projectivity? And we can take those samples and calculate the dependency length of each of those samples. And we can plot that in the same space as our real dependency length. Here it is. And we can then say, okay, this is the average dependency length per sentence length in the random projective baseline. This is what the dependency length of English would look like. This is what the curve would look like if the only constraint were projectivity. And, taking the real empirical dependency length curve and the purple baseline curve here, we see that the actual dependency lengths are shorter. So actual dependency length in English is shorter than you would expect from only projectivity as an independent constraint. And you can go on and come up with more and more random baselines instantiating more and more different possible constraints you think might exist on the tree linearization other than dependency locality. And you can plot them in the space, and you find that indeed the actual dependency length in English is shorter than you would expect under basically any of the random baselines that we tried. And now we can take this method and apply it to 54 languages from universal dependencies. And when we do that, we see the same pattern in every single language. So in every single language, the actual dependency length is shorter than you'd expect from all the different random baselines. Now, I find that people enjoy looking at this plot and speculating about what's going on with the different languages. So a few words about that. You'll notice that all languages have dependency locality. They all have shorter dependencies than all the random baselines, significantly so. But they vary in the extent of the optimization. So take English, check out English there between Dutch and Estonian. It is highly optimized. The black line is quite far from those colorful baselines. Whereas look at, say, Korean or Latin or German or Persian or Mandarin. Those are also optimized, but not as much. So what I think this tells us is that there are other constraints that interact with dependency locality, such that in those other languages, dependency locality is just relatively weak in terms of its aggregate effect. Again, all languages do have the black line below the baselines. They differ in the extent to which they are below the baselines. And this is, we've done lots of follow-up studies on things like how this is affected by things like morphology. I'd be happy to talk about that in questions. For now, though, the point is just that viewing human languages as a subset of possible communication codes, viewing word orders as a subset of possible tree linearization algorithms, we found that words that depend on each other syntactically are close to each other across languages. A dependency locality effect, an effect of this limitation on our working memory in language comprehension and maybe production, an effect of this limitation of our working memory on the word orders in our languages. Dependency locality allows us to minimize the memory resources that we use during language comprehension.